All right, if you're still working on that warm-up problem, let's switch gears and do our notes for today. And then, like I said, this is going to be a pretty short lesson. You'll have some time at the end of class to start the assignment or to finish up that problem. I would highly encourage you, if you have not finished that problem that we did at the beginning of class on your own yet, that you do finish it up and give me an opportunity to help you out if you're getting stuck or if you're finding you're making some mistakes. My advice to you on this, and it's going to be the same for the Poly project, which I'll be posting later on today. If you're trying to get this done in an efficient amount of time, you want to kind of slow it down a little bit and be careful, because there's a million places to make mistakes in this process. And what ends up taking you a long time is when you do make a mistake and you don't get a remainder of 0, and you got to go hunt that down. So I will purposely slow myself down a little bit when I'm working on these problems, just because I know it's a lot more time consuming to find a mistake than it is to go slow and not make any mistakes. Double check everything as I'm going. All right, y'all ready for complex numbers? Woohoo! All right, let's talk about the imaginary units first. So again, I really dislike this word. I wish they had come up with something other than imaginary, because it makes it sound like it's something out of a fairy tale and just totally made up. But it is super, super useful. Any of you who are going into hard sciences or engineering are going to be using imaginary numbers all the time. What we do with computers and mechanical engineering and computer engineering would not work without this mathematics. So they could have come up with a better name, in my opinion. But the idea of it is that there is a number called I that if you square it, you get -1. That's kind of the basis of the whole thing. I'm frozen, I'm sorry. There we are. So the imaginary unit is called I, and the definition of I is that I squared is equal to -1. Which means that I itself, it would follow, is the square root of -1. This isn't super important, but I did cut this out of your assignment, so I want to go over this with you. I didn't leave space for it on the page, but just in case this comes up later on. Because of this, we can do some interesting things with powers of I. So if I get your attention while I'm going over this, you don't need to worry about writing it down, but it does come up. It could potentially come up next year in calculus. And if you've seen it once, then you'll be good to go. So I to the first power is the square root of -1. Agreed? And then if I do I to the second power, I would just multiply this times itself, right? And I would get -1. So far, so good? What if I do I to the third power? That means I would need to take I squared and multiply it by another I. So I'm taking -1 and multiplying it by the square root of -1. What am I going to get? I'm going to get the negative square root of -1. Right? I to the third is just I to the second times I to the first. I'm just multiplying these two things together. So we're still going to have a square root of -1. It's just I'm multiplying by -1, so it's going to be negative square root of -1. Are we okay? What happens if I multiply that by another copy of I? So I'm going to end up with negative square root of -1 times the square root of -1. And when I multiply the square root of -1 times the square root of -1, it's going to turn into -1, but I still have my negative out in front, so I to the fourth is actually +1. And that makes sense to me in another way, because I to the fourth is the same as I squared, right? And I squared is -1. -1 squared is 1. Question? Yeah. So then we go to I to the fifth, and we're going to take this, and we're going to multiply by the square root of -1, which is the square root of -1. And then as we keep going, can you see how this is just going to end up repeating itself? Because we're constantly going to be just looping through these 4. So there were some problems on the assignment. I cut them out because a lot of our of my Blue Day students are going on that Seattle field trip. Any of you guys doing that tomorrow? Going down to the college fair? Yeah. So a lot of them are going to be missing class tomorrow. So they asked for a slightly shorter assignment, and I gave them what they asked for. So thank them that you have a slightly shorter assignment today. But there's some problems on the assignment that were like, find I to the 83rd power. Well, if you know this pattern here, then we can figure this out pretty quickly. Because I could look at this and say, so what I know from this is any power of 4 is going to give me 1. Any power of 4 is going to give me 1. So I would say this is not power of 4, factor of 4, multiple of 4. I would say this is I to the 80th times I to the 3rd. And I know that I to the 80th is what? It's 1. It's got to be 1 because any multiple of 4 is going to give me 1 always. And I know what I to the 3rd is. I to the 3rd is negative square root negative 1. So that's going to end up being my answer for this. Does that kind of make sense? So if I asked you to find I to the, 162nd power, you could do that pretty quickly, right? You'd say that's just I to the 160th times I to the 2nd. Why do they break it up that way? Because I'm pretty sure 160 divides by 4, which means that this piece here is 1, and I know that I to the 2nd is negative 1, so negative 1 is going to be my answer. Neat, huh? Okay, enough of that. So that's I. We played around with I. So complex numbers, the standard form of complex numbers is A plus B times I. And I'm going to ask that anytime you give me a complex number in this class that we give it in this format. I is its own separate thing. A and B have to be members of the real numbers. So they can be positive or negative, they can be 0, they can be fractions or decimals, they can be irrational things like square roots and pi and that kind of stuff too. This translates to is a member of or belongs to the set of, and this is how they type the double bar R. That's the real numbers. So in typeface, it looks like this. When we write it like this, but that's what it looks like if you print it. So this just says that A and B both belong to the set of all real numbers. All right, let's do a couple problems. So we're going to start with just simplifying radicals. So I've got the square root of negative 121. I can take the square root of 121. It's 11, right? But that negative is just going to cause us to have an I there as well. So I'm thinking of it in two pieces. What's the square root of 121, and then what's the square root of the negative 1? What's the square root of 18? It's going to be irrational, so let's simplify 18. I'm going to break this up. This is negative 1 times 18 can be split up into 9 and 2. And I'll just take the square root of each of those pieces. So I'm actually going to start at the end here, square root 2. In front of that, I'm going to have the square root of 9, which is 3. And it's also going to have an I in it. We'll put the I at the end. So 3 root 2 I. Yes?
What's stopping you from leaving the negative 2 in the square root?
We're simplifying, I guess. So in simplified form, we'll never leave negatives on the inside. We'll write them as a complex number in the standard form of complex numbers, which means the I comes at the end.
Could you also write it as 3i root 2?
You could write it as 3i root 2, but it would no longer be in standard form. So if the instructions say put it in standard form, then the I needs to come at the end. Yep. Mathematically speaking, 3I root 2 is the same thing as 3 root 2I. But this is not in standard form. The whole idea behind the standard form is to make it really easy to quickly see what's my real part and what's my complex part. If I look at this, my complex part is 3 root 2, but I have to look on both sides of the I to see that. So that's the whole purpose of standard form. I don't think 13 we can do anything with, so we would just call this root 13 and stick an I after it. The I could come before the root 13, but that wouldn't be standard form. So, am I going to take points off for that on a test? It depends on the instructions. If the instructions state to put all answers in standard form, simplified and in standard form, then the I needs to come afterwards. All right, so far so good. Adding and subtracting is really simple. It's just combining like terms. So if I'm adding these two complex numbers, I'm going to add their real parts together, 5 and negative 3, that's 2. And then I'm going to add their complex parts together, negative 2I and negative 8I is negative 10I. That's it. Subtraction, same thing, except you got to be more careful with your signs. Don't forget that this negative goes on to both of those. We'd have 5 minus negative 3, that's 5 plus 3, or 8. And negative 2I minus negative 8I, so that's like plus 8. Negative 2 plus 8 is positive 6. Yes? Why do we do it in standard form like that? So you may end up with something really complicated in the future, okay? So you're working on some engineering project in your senior year or something like that, and you have some poles or some zeros that involve complex numbers, and maybe you end up with a complex number that looks like this, like root 72 sine of 2 plus x squared cosine root 85I. Okay, something really, really ugly and messy like that, right? But the important part of it is when you're looking at these things, the real part of the root is going to tell you one thing, and the complex part is going to tell you something else. And if we put it in this standard form, even when this stuff starts getting complicated, it's really easy for me to see where my real part is and where my complex part is. The thing that has the I at the end of it is your complex part. So that's the whole purpose of it. We do the same thing when we're doing radicals, although they don't push that as much anymore because I don't think square roots freak people out as much as they used to because of computers. We have computers that can do all that. And in the past, square roots were kind of a mess. You had to use tables or a slide rule to figure out values for square roots. But whenever we did the quadratic formula, we would always have it be two separate things. We would never write 3 plus or minus 2 root 5 over 6. It would always be 3 over 6 plus or minus 2 over 6, and then the root 5 would be separate from it at the end. Yep. Does that answer your question?
Yeah, now I have another.
Okay, it brings up another one. Yeah, what's that?
With that equation that you wrote down,
This thing?
yeah, if you wanted to graph that, what would you do with the I? And also, since it's both waves, like the two waves amplify each other?
No, this would be, I just kind of made stuff up out of thin air on this. When you do graph complex numbers, which we're not going to do in this class, we graph them on the real complex plane. So let me give you a simpler example. If we had the complex number negative 3 plus 2i, this is no longer the xy plane, this is the real complex plane. So negative 3 plus 2i would be this point on the complex plane. So if you're using complex numbers in an equation that has x's and y's, you've introduced another dimension into the whole thing. So it would be a 3-dimensional graph. So it'd be a surface instead of a curve. And that's way beyond what we're trying to talk about in this class, and beyond the limits of what I still remember from my time in college. But yeah, so the clever thing, and thank you for the questions, by the way. The clever thing about complex numbers is they allow us to squeeze two dimensions into one number. That's why they're so useful. That's why we use them so much in mathematics, and especially in engineering applications, because it's pretty common that you have to deal with kind of two different things at the same time. Complex numbers allow us to deal with two different dimensions in a single equation. So some examples of some different dimensions that I've run into before. So a lot of times you want to talk about the amplitude of something and then also the frequency of something. So an example would be like like a vibration in a car engine. Like how much is it vibrating? How much is it bouncing up and down? And then also how fast is it? How often is it bouncing up and down? Right? A car engine is going to have certain vibrations in it, and they put structural things in there so that you don't feel those vibrations inside of the car to kind of hold everything steady for where you're seated. So they would look at these complex equations that would predict the best way to dampen that, and they would all use complex numbers. So anyways, all right, can we get back to the nuts and bolts? Thank you for the big why questions. I think those are important, right? Why am I learning this? Because someday you might be designing something where you need to deal with it. Any kind of radio, telecommunications, that kind of stuff uses the same math too. All right, let's talk about multiplication. When you're multiplying, if you're multiplying a real value times a complex value, it's just distribution. So you would just distribute the 6, and you would get negative 18 plus 24i. If you're multiplying two complex numbers together, hi. Oh, thank you. Gotcha, thank you. If you're multiplying two complex numbers, it's like FOIL. Yes? What a wonderful question, thank you. Could we simplify and factor this out? Yes, I could factor out, what could we factor? A 6 out of that, right? So if I factored a 6 out, I would end up with negative 3 plus 4i. That is absolutely the same thing, but it's not in standard form. Say that one more time. This is standard form. So standard form wouldn't have any parentheses in it. Yeah. So we could factor it, but if I'm asking you for an answer in standard form, I'd say just leave it alone. You're done when you get a single complex number. A single complex number is going to have a value for the real part and a value for the complex part, for the imaginary part. And they're clearly distinguishable because one's got an I attached to it and the other one doesn't. Yep. Great question. Thank you. All right, I'm going to let you guys do this however you do it. I'm a big table fan when it comes to multiplying stuff out, so that's how I'm going to do it. But if you guys do FOIL or if you do the little double rainbow trick, whatever works for you. You guys, what do you call that thing, the double rainbow? You know what I'm talking about? It's like this and this. It's just foil. It's all foil. It's I know of like 5 different ways to do this, and it's all foil. Have I showed you face before? I learned face in high school. This is what they taught me. There's 2 eyeballs and a nose and a mouth. This is face. You see the eyes up here? And a nose and a mouth. It's the same, but it's the same thing. It's foil. You're just multiplying all the different things together, right? It's the same thing. But as I've gotten older and more scattered, I find that the table keeps me from screwing things up. So that's what I always do. We're going to end up with a negative 10. We're going to have a positive 6i and a 5i. And then negative 3i times I is negative 3i squared. And then what I'll usually do is circle this thing and change it into what it actually is, because I squared is negative 1. So negative 3i squared is positive 3. Right? It's negative 3 times negative 1, which is positive 3. So my final answer, if I combine my like terms, is negative 7 plus 11i. Is this feeling okay so far? Do you guys remember this being like a lot more difficult last year? Sort of. Often when I mention we're doing complex numbers, people were like, "Oh, that was hard last year." I think sometimes it's just because it's the first time you've seen it. All right. I know you talked about this last year because I've heard a few of you use this term already this year. You guys remember what conjugates are? So conjugates are binomials that are the same, except the second term has its sign flipped. So complex numbers, kind of by their nature, make a binomial. There's two terms. So if you've got a complex number, its complex conjugate is going to be the same thing, except the imaginary part sign will be flipped. So the complex conjugate of 2 minus 5i is 2 plus 5i. It is only the complex part that flips its sign. So if I had negative 3 plus 2i, the negative 3 would stay the same. It's the positive that would change to a minus. We want to know about complex conjugates because they can make our life easier for some of the stuff that we're going to have to do. Because they've got a really useful property that says if I have two complex conjugates that are being multiplied together, my answer is going to be entirely real. There will not be any i's in the answer. And to figure out what the answer, the product of those two things are, just square your real part and square your complex part. Add them together. You square the i's, which turns into an I squared, which is a negative 1, which is why this is a plus instead of a minus. Normally when we did multiplying like this, where there was a plus and a minus, this would be a minus over here. But it's the i's getting squared that turns it into a plus. Right? So when I'm doing this problem, I'm not going to build a box for this. I'm going to look at this and say, oh, those are complex conjugates. My answer is just going to be 2 squared plus 5 squared. It's 29. All right, 4 plus 25. Same thing here. I'm like, oh, those are complex conjugates. I don't need to do work. This is going to be easy. Negative 3 squared is 9, and 2 squared is 4. 9 plus 4 is 13. 13 is what I would get if I were to multiply those two things together. So complex conjugates are really useful to us because when you multiply them together, you're going to get a fully real answer, no complex part to it. And that's useful because there's a rule when it comes to fractions. This is another one of those old rules that is around because, because probably it was invented when there weren't computers to make life easier for us. But we still follow it. If I had something like this, I would always simplify it. I do not want, first of all, it's not in standard form. So I need to get this thing into standard form, which means the first thing I got to deal with is I don't want complex numbers in my denominator. I want my denominator to be entirely real. If I can get this and change it so my denominator is entirely real, then it's super easy to turn it into standard form. So how are we going to do that? Fancy one, good old fancy ones. We know a trick. We know something that we could multiply 2 minus I by so that it was no longer a complex number. It was fully real. And that is what? 2 plus I. Right? That's the conjugate. And the useful thing about conjugates is when you multiply two complex conjugates together, we're going to get a fraction that's going to be entirely real on the bottom. There won't be no more i's, which is what we want. Now, we're going to have to multiply the top by 2 plus I also, which means we're going to end up with complex stuff in the top, but that's okay. That's going to be easy to deal with, as you're about to see in a second. So let's go ahead and do this. Bless you. We got 8 plus 4I. And down here, we're going to square the 2's. And we're going to square there's a 1 in front of that I. So we'll square the 1's. Is that a 5 on the bottom? Is that what you guys are seeing? 8 plus 4I over 5. All right, that's not in standard form yet, but it's really easy to turn that into standard form.
Why is it 8 instead of 6? No, but, what am I saying? Never mind, sorry.
I think, yeah, you got it. No. It's easy to mix those up. It's all good. All right, standard form. So just split it into 2 fractions. 8 over 5 plus 4 over 5. All right. That would be our final answer.
I always have to be separate.
In standard form, yes. I needs to be separate from, it needs to be very clear that this is my coefficient on the I. So we don't want I to be part of the fraction. We don't want I to be stuck inside of a square root. We're going to do what we got to do so that we can clearly and quickly see what's the thing being multiplied by. We don't want things on both sides of the I. Yeah. All right. Try that last one. Same idea. We're just going to multiply this by a fancy 1. I don't like that this is a complex number in my denominator, so I'm going to force it to be a real number by multiplying by its conjugate. So in mechanical engineering, when I was talking about how we use complex numbers to talk about frequency and amplitude, and we were talking about plotting complex numbers on a real complex plane. There's rules about, so you can model a physical situation using these things called transfer functions. And transfer functions look a lot like rational functions, which we're going to get into after this. Factored stuff on the top and factored stuff on the bottom. And those factors will give you with things that are called zeros and poles. We're gonna refer to vertical asymptotes instead of poles. But there's a rule that those zeros and poles, if you graph them on the complex plane, as long as you don't have any poles on the left-hand side of the plane in quadrants 2 and 3, that it should be a stable system. Unstable systems will have poles on the left-hand side. I think I'm getting that right. I might have it backwards. But an example of an unstable system would be have you ever seen the video of the Tacoma Narrows Bridge? It's old. It was a bridge that was built like in the, oh man. And it shakes. It's like shaking back and forth. It's terrifying. And it just collapsed. So the wind hit it one day, and the whole bridge collapsed. I'll pull up a YouTube video of it. I bet you've seen it before. But that's what happens when somebody doesn't understand complex numbers. Bridges collapse, and luckily nobody was injured on that whole deal, because it started and people were able to clear off of it for a while. You'll see on the video for a while, people were like hanging out on it, like, "Ooh, this is fun," before they realized, like, "Hey, maybe this isn't a good idea." All right, that's all I got for you for complex numbers. You guys got time to start on the assignment? I'll put it up on the screen here.